Hello, my name is Parente and I'm going to present an article with the title Fatigue Behavior in Graphene Composites, an overview. So let's start with an introduction. Nowadays, nanoparticles are applied in many engineering applications due to their unique surface effects, increased chemical activity, and physical properties. Among the nanoparticles used, graphene is one of the most promising due to its excellent mechanical and electrical properties. Higher mechanical properties can be obtained when graphene is added to polymeric materials, and since it's a strong material, they also prevent crack propagation. This last benefit is very important in terms of impact response and fatigue life. Most of the studies are about the static characterization of graphene-reinforced materials, although there are some about fatigue performance. This phenomenon is very important because failures originated by fatigue may have tragic consequences, especially in railway, aircraft, and process industry. Therefore, research on fatigue contributes to reduce the probability of accidents and disasters. But what is graphene and what types of graphene exist? The most basic type is called graphene nanosheet. It consists on a single atom thick carbon honeycomb structure in a lattice formation forming a sheet-like surface. It offers improvements in the tensile strength and stiffness, thermal stability, electroconductivity, and viscoelastic properties. The second type is called graphene oxide. It consists of graphene nanosheets with added oxide-based groups. These groups improve the interaction with the matrix by forming stronger connections, and they also offer anchorage points for the creation of functionalized graphene. The third type is called graphene nanoplatelets. They are composed by several layers of graphene sheets connected by van der Waals forces, one on top of the other. They possess a large overall size, offering a high contact area. This allows the creation of materials with better mechanical performance, especially in fatigue performance and impact performance. Knowing this, the objective of this work was to see what articles about fatigue have been published so far and what results were obtained by the different authors. So, we divided this work by the type of material enhanced with graphene. Of all the materials modified with graphene, the resins are the ones with the biggest number of articles published. These resins consist of epoxy, a material that is easy to manufacture, making it an ideal subject to study the addition of graphene. In this type of composite material, the most important aspect is the interaction between the matrix and the graphene, the dispersion of graphene in the polymeric resin, and the orientation of this nanomaterial in the matrix. During the period between 2009 and 2019, there have been a total of 11 articles published about fatigue behavior in graphene-reinforced composites. Overall, there were a 25 to 1,580% improvements in the fatigue performance between all the articles. The table to the right shows the main results obtained. In the article, we were able to conclude that the main failure mechanisms in resins was crack propagation. So, in a resin reinforced with graphene, as the crack propagates in the matrix of the resin, it will eventually hit the graphene. This will force the crack to go around the graphene, creating smaller cracks and decreasing its energy. This is why the orientation of graphene is important, since graphene oriented towards the crack tip will force the crack to steeper angles and thus have a stronger effect in decreasing its energy. The second type of graphene reinforced material with fatigue articles is elastomers. Elastomers are materials that have the ability to return to its original shape when exposed to a load. The addition of graphene to elastomers has the ability to increase its toughness and thus decrease the effects of crack propagation. The failure mechanism of this material is similar to resin. A total of 6 articles have been published between 2013 and 2020. Of these articles, the results show that the application of graphene has the ability to improve the fatigue life of the material, with some articles showing an improvement of 38%. The majority of tests was carried out by crack propagation fatigue tests, since in regular tensile fatigue tests, this type of material lasts the total amount of cycles. As we said before, the failure mechanism in elastomers is similar to resin. In the figure, you can see the evolution of the crack in a fatigue test. As we can see, it is possible to observe the deflection and the splitting of the crack that occurs due to the presence of graphene in the material. Laminates are another type of graphene reinforced material. Laminates consists of a polymeric resin and a fiber reinforcement. This fiber reinforcement is usually made of glass, carbon, basalt, or other type of fiber-like material. This creates very strong materials that can be further improved with the addition of graphene. In the study of fatigue, the interaction between the graphene, the fiber, and the matrix must be considered, since a non-ideal interaction between these three can decrease the overall performance of the material. From 2010 to 2019, 5 articles have been published about the incorporation of graphene in the laminates. The majority of the articles published focused on the use of carbon fiber laminates. A resume of the results can be seen in the table to the right. In laminates, the failure mechanism is similar to the resin composites, although the presence of fibers creates new challenges. In this type of material, the size of the graphene is important, since graphene with great dimensions may create weak interactions between the three types of material. The figure indicates some of the problems that can occur with large dimension and small dimension graphene. These problems include plastic voids, crack deflection and bifurcation, and interface failure. Graphene can be applied to other types of non-polymeric materials in order to improve their mechanical and fatigue properties. These materials consist mainly of metals, ceramic, and aerogel composites. In the case of metals, like the polymeric composites, the addition of the graphene to the matrix as well as its dispersion is of the most importance. A bad dispersion of graphene in metal can lead to the creation of graphene agglomerates and voids, which lead to weaker material. In metals with added graphene, very few articles have been published. This is mainly due to the difficulty to create composite materials that mixes graphene and metals. Of all the articles published, the best results are in the order of 160%. A few articles show a deterioration of the results in this kind of material. This is mainly due to the formation of voids during the manufacturing process. Like previous materials, the main failure mechanism in metals is crack propagation. Since metal is a more strong and homogeneous material, the cracks are going to start by the defects in the graphene that were created during the fabrication process. These defects, which include voids and agglomerates, create areas where the initial cracks can start and then propagate towards the material. The last and more recently developed material is called aerogels. Aerogels are usually composed of carbon nanotubes which are coated with graphene. This coating leads to a tougher material, improving its fatigue performance. More recently, a new type of aerogel composed entirely of graphene nanoplatelets was developed, with a better fatigue behavior than other types of carbon-based aerogels. Literature reports several studies on the fatigue behavior of graphene composites. However, existing knowledge is not yet enough to establish a complete understanding of this subject. In general, it can be said that graphene acts as a block in the crack propagation path, forcing the crack to bypass graphene in the path of least resistance, delaying the crack increase. We can also conclude that the interface strength between matrix and graphene plays an important role because low adhesion facilitates crack initiation and propagation along the material. We can also conclude that aligning graphene fillers perpendicularly to the crack growth direction promotes greater benefits on the fatigue strength than those randomly oriented. As a future work, there's still a need to study the fatigue behavior of composite materials filled with functionalized graphene and compare it to pure graphene. The open literature also does not report studies on the benefits of graphene fillers on the mechanical properties of composite sandwich structures, especially on the fatigue strength. That is all. Thank you for your attention.